do other stuff. I'm happy to click. Yeah,
Where's the clicky thing gone?
It's there, but I'm plugging that in my computer. But you can. I'm not doing that. No. That's crazy stuff.
So you're just gonna have people say next?
Yeah,
And you
just
push the button. Okay, cool.
Yeah, and you can use this for the pointy bits.
The laser.
All right, we'll leave it over there. If you want to use it, you can use it.
So in that box, we have the external circuit now.
Yeah.
And it's called IETF external and IETF 120. And then I've written some Python, which goes through and pulls all the circuits that are marked external.
Yeah.
And puts those into the templated config and the BGP config. And so like we can, when you put a thingy in, you just add it to Netbox and it builds everything. Wow, apparently it's already recording what I'm saying.
Good morning. Oh yeah.
Is there nothing on the display, or does it, like, maybe it's the other side?
There is. It says there's no battery.
Great. This one? Yeah, it's busy like recording everything I say and transcribing it, which would have been good if I'd, known that before rambling on for a long time about clicky things. What size battery does it take? Probably doubles.
Oh, wait, there's another one of these.
I will tell Meet Echo that we need another battery.
Okay, battery works now. I feel super old. I was expecting it to be like some USB-C plug thing, whatever.
So you stole it from another mic or from the table?
It's on the table. Good morning. This is the IEPG at IETF 120. Somebody's going to complain that we have, I don't know, agenda slides or something, but we do. So just before we get started, you can flip forward. Oh, you probably have to. I'll do it in a second. Anyway, before we get started, if you're up here presenting, please either use the stand and look at the people. Or if you don't want to do that and you want to do this, you can walk around. I wouldn't do this. That's bad. Definitely don't do this because no one can fucking hear you. So speak into the mic. If you need guidance on how to do that, hold the mic like this, and then everyone will always hear you. Okay.
Next slide. There we go. So, hey everybody, this is what the IEPG is. It's an informal gathering that meets on the Sunday prior to the IETF meetings. In theory, it's all supposed to be operationally relevant content. And I think this time most of it is. And for once, our agenda is not filled with BGP and DNS. Chris stole it from the back, but so we just need a replacement for on the table. Yeah. So Chris has now disappeared, so I can't actually show you what the agenda is, but it's very nice. I can tell you what the agenda is. It is IPv6 over Bluetooth, and then network and sustainability and ops perspective, experiments in post-quantum DNSSEC, migrating Latinx RPKI, and then IP in deep space. I believe that that's everything that people had offered, and so we will jump into it. IPv6 over Bluetooth, we're actually going to do first. So that is Nalini and Rakshith. Who's actually going to be presenting? Is that going to be remote? Rikshi, okay. So that will be a remote presentation, I believe, because of Visa Entertainment.
Unfortunately, yes.
Is great.
Yep, he's
She
on.
is up.
Okay, I'll do a quick introduction. Ready? Okay. So this is part of a larger grant that we are doing for internet resilience and disaster recovery on a shoestring, very low, so we can do it ideally under a $10,000 kind of a budget, which makes it very in the reach for many people. So, and this is one part of it. Rakshis, please go ahead.
I think she's muted.
Am I audible and visible?
Yes, yes, we can hear you now.
Yeah, thank you. Yeah. So, hi everyone, I'm Rakshit, and along with me, Srinidhi Tejas, under the mentorship of Nalini, I've been working under this. We are from NITK Surathkal. So, the topic is IPv6 over Bluetooth for power affluent devices. Um, Next slide. Can I go to the next slide myself or have to inform you?
If you want to share the slides yourself, you can do that. I'll stop sharing and then you can try. How about that?
Yeah, sure, that's fine.
Stop. Yeah.
Okay. Is this visible?
No.
No, hold on.
Oh.
It's, just to share the screen. That's slides control.
Yeah, I think it's coming.
Okay. Okay.
Yep, we see it now, Rakshith.
Okay. Thank you. Yeah. So, an overview. So, what is IPv6 over Bluetooth to those unfamiliar? It is basically an extension that allows you to use IPv6 over Bluetooth, that is, transmit IPv6 packets over Bluetooth. And this started off and has been mostly confined to communication in IoT networks, based mostly due to the low energy consumption of Bluetooth, and it is also known as IPv6 over Bluetooth low energy for that reason. And in this presentation, we propose to discuss its use for power affluent devices. That is a technical way of saying not resource constrained. That is, everyday devices such as phones and laptops and PCs and so on. And the objective is to achieve connectivity during internet failures. Yeah. So this is a brief description, a pictorial description of how IPv6 over Bluetooth would work. Um, is my audio clear?
Yes, we can hear you, Rakshith.
Yeah. Yeah. Right. So suppose we have a sender and a receiver who are running some network application on IPv6. We have an IPv6 over Bluetooth stack that can contain many components. So the idea is that once IPv6 packets are outgoing, they are intercepted by this stack and they are passed to the Bluetooth stack, which then sends it over to the Bluetooth on the other device. So there is a Bluetooth link, but IPv6 packets are being sent. IPv6 packets, in other words, is the data of the Bluetooth packet, and the receiver passes this packet to the IPv6 over Bluetooth stack, and then that those IPv6 packets are then extracted and given to the network stack, TCP/IP or UDP or whatever, and then passed on to the relevant network application. So this is how two devices would communicate. Of course, there can be intermediate devices in between. Right. So that was a brief description. So coming to the use cases, so all use cases are for internet unavailability, and one of the most common occurrences is during disasters. So disaster more often than not disrupt traditional means of communication. You don't have the internet, phones, cables more often than not. So in such times, establishing communication and coordination so that rescue teams can contact people and communicate with them is extremely important. And having an alternate technology to have a local network where you can communicate with each other is very important. And IPv6 over Bluetooth can be used for exactly this reason. And especially small and medium sized communities, for example universities, right, or those who want to have a backup plan in case of frequently occurring disasters, can make use of this technology. Right. So there are two RFCs, RFC 9159 and I believe 7668, which discuss this for IoT devices, that is Bluetooth Low Energy. And so, how would a network look like when you have a disaster area and you're using IPv6 over Bluetooth. So there can be devices with different roles, nodes, routers, or both, and border routers. And border routers in this technology are those routers which can give you access to the internet and connect the local network to the internet. So better explained with this picture, right? So you have devices, maybe laptops with different OS. Um, yeah, so they're acting as nodes. Nodes basically participate in the network. Routers route packets to other devices, and border routers connected to the internet. So if you don't have a border router, you can simply communicate with devices within the network. So that is the objective, right? So yeah, continuing, chat applications. So Bluetooth chat initially gained prominence through the Bridgify app during the Hong Kong protests. There, it was the case of internet shutdown. So we have a similar idea, that is, use IPv6 over Bluetooth to send messages from one device to another across multiple hops in the network, right? And then IoT gateways. So this is not a power affluent devices use case, but we thought of mentioning it. Suppose you have multiple IoT gateways that are communicating with each other, or maybe communicating with the central router. You can have this as a fallback mechanism in case Wi-Fi connection or cable connection or something of that sort fails. Right. File sharing. Again, Bluetooth has developed a lot since its version 1, both in range and speed. I believe initially it was a few hundred kbps and now it is a few mbps. It can go up to tens of mbps. So IPv6 over Bluetooth can therefore be used for file sharing in local networks, basically transfer files from one device to another. Next, local network notifications. I believe this is the most important of all, especially in a disaster area where you want the rescue teams to send updates to people, right? For example, weather updates and notifications about a particular event, or a food delivery, or a medicinal supply delivery, or so on. So you can use this to broadcast information from uh, the team to the people across multiple hops across the network, so that it reaches everyone in that particular area, right? And the last one is data backup. So supposing you detect low signal strengths or internet unavailability during the early stages of a disaster, you can think of backing up your data, and you can either use the actual internet through a border router and back it up on the internet itself, or you can back it up on multiple devices or designated devices in the network that are probably a little far off from the area where the disaster is going to happen, or something like that. So this is another use case. So overall, the focus is to use IPv6 over Bluetooth for local connectivity during internet unavailability. Yeah. So coming to a little about implementation. So we have been testing an implementation on Windows 10 about the IPv6 over Bluetooth stack. So it consists of a few components and a few libraries. So this is a brief description of that. Firstly, the important task is to take IPv6 packets that are outgoing and send it to Bluetooth. And then the other task is to take IPv6 packets from Bluetooth packets and send it to the network stack. So we need a driver or an OS level module to do this. That is one thing. And another application that can be a central component that can interact with the driver, obtain device addresses and find nearby devices, connect to them, and so on. That is what we are calling as a packet processing application. So these two are the main components. And this packet processing application makes use of different libraries. Um, that is a driver interoperability library, and a GAT library, and a 6LoWPAN library. The first is to interact with the driver, a user space library to interact with the driver. The second one is, to set up a GAT service. So basically, how do Bluetooth devices let other devices know that they support IPv6 over Bluetooth? So the IETF has developed a standard in the form of a profile for Bluetooth GATT servers, and that is called the IPSP profile, um, which says, yeah, so I support IPv6 over Bluetooth. You can send me IPv6 packets within Bluetooth, and I understand that. So that is something that is an essential thing. And we also have header compression and decompression. This was designed for IoT networks, but we can have this as an optional thing if we are doing it for power affluent networks devices. Sorry. So this is a description of again a pictorial description with the packet processing application interacting with the libraries in the user space, and in the kernel space with the internet stack, the Bluetooth stack, and the driver. So yeah. Uh, Coming to the requirements for setting up an IPv6 over Bluetooth network, what all would we need? Firstly, you need to have that stack in your device, that is a driver or and an application to convert between IPv6 packets and Bluetooth, and a central component or something of that sort. So this is on the device as described in the previous implementation. And the other thing is you will need to configure routers to forward packets, and then you'll need to configure maybe a border router if you want to access the internet, right? And then last but not the least, the very important thing, to address devices, assign addresses to devices. And in the RFC, I think it has been proposed to use the EUI64, but again, it may or may not be used. We can use some other addressing mechanism or stick with that, right? Yeah, in conclusion, this is a IPv6 over Bluetooth is a viable solution for internet unavailability. And yes, there can be a few security and implementation issues, but we need to deal with that. And we can maybe go about setting a common set of guidelines and implementation details that can be useful when we are developing this on different platforms. So yeah, that's it for the presentation. Any questions?
Someone come to the mic.
Hi, thanks for a good presentation. My name is Jeff Haas. So you mentioned the security stuff, and that's one of my two questions. So the first question you'd mentioned, like example, Bridgify, it's an example of places where people want to have no good security. How far have you looked at security, for this type of application?
Uh, Shall I answer? Yeah, we haven't started with that, to be honest. We are just looking on testing, getting it to work between two devices and all. But yeah, I think there are some security concerns given in the RFC as well. We will need to look at that. Yeah.
Yeah, Rakshit, I'm going to jump in there too. Totally good point, uh, uh, Jeff. Right now, we're trying to just make it work.
Okay.
But yeah, totally point taken, because as you say, some of these situations are delicate,
Yes.
and one wishes to have very good security. Yeah.
Okay, well, in that case, my second point also maybe is in your wish list. So one of the challenges you have whenever you're doing these sort of low bandwidth applications is if you have a generic device that just says, I have IP reachability now, having a prioritization scheduler to control what can use that bandwidth can be very important. My favorite example of that is your laptop just got on through a modem and it decides, from your IT spyware to run your backup right now, and you can't actually get your email through.
Yeah, really good. Rakshit, did your team hear that? We need a good workload scheduler and prioritization. Yeah,
Yeah,
really.
yeah.
Yeah. Super good points. Yeah.
Another Jeff. Thanks for the presentation. I was kind of interested to what extent this work, it seems to be very much in parallel to the MANE work that's been going on in the IETF for almost 10 years. To what extent does this intersect with the MANE work, and why isn't it, I suppose, using that entire framework? To what extent and why are you heading off in a different direction if that's what you're doing?
Rakshit, let me grab that one too, and then you can.
Yeah.
Fun, yeah. So yes, indeed, there's a number of different alternatives. One of the things we went into is like, I'll give you just a little example. I was talking with some of our folks in the military, and they have like 18-year-olds. They jump on the thing. On a, they go to the Philippines in a typhoon, whatever, and they're just having a nightmare setting up the whole communication system. What we're aiming for is something that very, very, shoestring, very little technical knowledge, needs to be done. My Rotary Club can do it. You know what I mean? And some of these technologies, excellent as they are you need a technician. That's kind of where we were coming from it, Jeff.
So you're saying Manet has a much higher configuration load?
I think so. I think, and it definitely, we need to look at that. But that's what we felt. And even setting up Wi-Fi and a wireless access point, that kind of stuff. But really good point, Jeff. We'll go. What we should do is do a comparative. You know what I mean? How long does it take us to do this versus Manet?
There's been a lot of work in Manet.
I
It's
know.
covered a huge amount of ground, so it's not a slight thing. But the reason why there's been a lot of work is that it is an interesting problem to solve, this mobile ad hoc network.
No,
And
totally.
that's exactly what you're doing here.
Yeah,
So I
yeah.
was just wondering why a different path. But okay, fair enough. Thank you.
No, totally get what you're saying, and I know some of that work too. Mhm.
Hi, Bob Hinden. Two comments. I find the title of this draft doesn't really match what I think you're trying to do, because I read it as sort of trying to be a protocol spec or something, which that work is already done. So you might consider, I mean, I think you're trying to use Bluetooth for simple ad hoc networking. So, in certain environments. So you should make the document, make it clear that's what the document is about. And then, as I said, this on list, the section on shortwave radio shouldn't be in this document. It's got nothing to do with Bluetooth. It's a whole different topic.
No, totally get that. And this is, as I say, what we've done is we've kind of redone the whole thing for, as I say, a larger grant in this area. But the grant is for disaster recovery rather than a protocol spec. Yeah. Yeah, yeah. No, really good point. Really good point, Bob.
Hi there, Tom Hill from BT. Thank you, Rakshi. Lovely presentation. Forgive me if this is quite a basic question. I'm struggling to work out as to whether or not, and I don't do a lot of work with Bluetooth, you'd be very obvious to find out, how much of this is actually new IP work and how much of it is implementing things that already work in IPv4?
I didn't understand you. I mean, you mean IPv6 over Bluetooth and IPv4 over Bluetooth, something like that?
You gave a UK use case about the mesh networking or messaging that was done in Hong Kong during the internet shutdown, and I
Yeah.
wondered, obviously that was working with something. So how much of this is implementing an IPv6 stack, and how much of it is implementing new capability in IP? Does it all work in IPv4 today?
No. So this is not about changing anything in IP. This is about building another stack that is an IPv6 over Bluetooth stack. Some more software that can help you give out IPv6 packets through Bluetooth. So this won't require any change to the IP stack or the Bluetooth stack, as far as I know.
Now, you know what? I'm sorry to
Right.
interrupt here. Okay, so where this kind of led from is like, if you look at the interfaces on Windows, you'll see that the Bluetooth interface has an IPv6 link local address. And it ends up being a bit more difficult to get an IPv4 local address. You can, but it's a different kind of address. So in this case, we were kind of going from there that it seemed easier to do IPv6 first on that stack. And that's, you see what I mean?
No, that's great.
Yeah.
Given the use cases that were mentioned, I thought this was all working in IPv4.
Yeah, that's a very, you can see here, there's a bunch of gaps here. This is really early. We need to, one of the things, other things we really haven't done is seen how much is working over IPv4. That is definitely a to do. Because I'm not, we need to put, Rakshit, we need to put up that Bridgify app, see what exactly they're doing. It's totally true.
Okay.
Yeah.
It was curiosity, so thank you.
Yep, yep. No, curiosity for us too. It ends up being a surprisingly large space.
Hi, yeah, thank you very much for the presentation. So given how you specifically said for non-energy constrained devices, so for energy constrained devices, I can see the immediate benefit of Bluetooth low energy, but for energy unconstrained devices, it is kind of competing with Wi-Fi direct, right, without access points. And so I was specifically wondering if you've tried to make a comparison and see why Bluetooth is more interesting than Wi-Fi. So the
Yep.
primary idea coming to mind was that the Wi-Fi may already be kind of in use for kind of trying to uplink to the internet that isn't working. So Bluetooth is available and not used or something like that. But so I was looking at your perspective.
Yeah, no, yeah, Rakshit, you want to grab that one?
No, you go on.
Yeah. So that is, no, we'd need to do a real comparison because I think it was ease of use that we were going down, it seemed like Wi-Fi to us required some kind of central point where this can be pretty much peer to peer. Yeah.
Lorenzo Colletti, can you go back a few slides to the sort of complicated diagram with lots of devices on it?
Rakshit, can you go back a few slides? Yeah. Oh,
Yeah.
that one, I think. Yeah.
Yeah. Okay, so this looks very cool, right? But it's actually quite hard to do, I think. So one of the things that are quite interesting here is like, how do you assign IP addresses? How do you do mesh routing? If you just do this, you basically end up with a routing loop, right? So I think that maybe sort of is what maybe Jeff was alluding to. Like, how do you make this work, right? Are you going to run Babel on all of these things? Are you going to, who's going to assign IP addresses and so on? Do you have any of this working, or is it just sort of aspirational at the moment?
We have some of it working. Between some devices. Yeah.
So have you done multi-hop yet, or
No,
not?
we have
I
not
see.
done multi-hop yet.
Okay.
Yeah.
So then, so
Yeah,
that
we have
you did.
single.
So
Yeah.
you did the easy part. Okay. Well, I mean,
it was hard enough.
yeah. Yeah. I'm sure it was hard. So yeah, I think that would be quite interesting too, because I think multi-link subnet routing is kind of really an unsolved problem, and I think Sixman has also been sort of struggling with this as well. So if you figure out how to make this work, let us know, or if you think Sixman can help. Yeah.
You know what? It sounds like we've got a couple of things. First, we want to at least make it. We only have it working on Windows. We want to at least make it work on Linux. And then I think what we should probably do is get the Bridgify app going, get the Manet business, and just see, where the gaps are. Because to us, it seemed like it was there's a bunch of gaps, and the ease of use thing needs to be thought about. But we need to actually go over to the Manet people too.
And these things, they have to have explicit pairings with each other, Bluetooth pairings, or because that's also sort of like high touch, manual stuff where you actually have to go to each device and like talk to them to configure.
That's a very good point. You know what? Oh my God. Yeah, I have another whole idea for explicit. I mean, oh my God. Now you're making me think about another whole approach to this. If I may have an idea for this. I need to think this out. But if you allow me to do explicit configurations, it really simplifies the problem a lot. The problem with explicit configurations is that solves the problem of for example, in internet shutdown case, Mr. Policeman or, Mr. Government, I don't know. I'm just babbling, but it keeps that problem out. But it brings up other problems of who do you let in if it's an explicit configuration. Anyway, there's a lot of work and interesting stuff. We're really at the edges of this, and we'll keep you posted. Sorry to talk so much.
Thank you.
Thank you.
Yes.
Rakshit, did you have something else?
Yeah, thank you.
Yeah.
Oh, there's somebody
No,
on
no,
the.
put it on the stand, please. Yeah. You can just tip it down.
Or you can hand it to me and I'll just hand it to the next person, who is Ali.
Ali?
There we go. And you've got 20 minutes.
Plus 5 for questions.
Yeah, I had 20. It was 20 with questions. Okay. Cool.
Good morning. My name is Ali Rezaki. It's my first time here at the IEPG meeting, so very glad to meet you all. Today I want to talk about sustainability, environmental sustainability from an operational perspective. You probably recall that the E-Impact program had started a while ago with the intention of investigating the environmental sustainability topics that could be relevant for the IETF. And this Wednesday, we have a green BOF looking at the mostly energy metrics of internet working. Now I want to share with you some further topics and hopefully collect your feedback. What would you prioritize from an operational perspective? Because sustainability is a deployment and operational impact question. Because we develop our products, we manufacture our networks, but at the end, what impact do they have on the environment is really out in the field. So this is really crucial. Next slide, or can I control? No.
Unfortunately not.
Okay, great.
We're waiting for it to change. It should be changing. There we go.
Thank you. I want to first share with you some valuable references. One is from our colleagues from Ericsson and one Nordic operator, and the other is from a co-work from the World Bank and ITU. And they frame quite well high-level terminology as well as global data that's important to understand the impact of ICT in general. So the data is at high level and therefore it is sometimes hard to trickle it down to what it means for certain protocols or network architectures. But overall, it gives us an idea. And one of those ideas is that the ICT sector is responsible in 2020, and it's roughly along the same lines, 4% of global electricity consumption and 1.4% of GHG emissions. So I'm assuming some level of terminology, greenhouse gas emissions and the rest. If not, please interrupt. So what it means is that electricity consumption translates into some level of greenhouse gas emissions. And that depends on a few things, which I will elaborate later on in the slides. But so far, as an ICT sector, I'll present what it means in the next slide, is responsible for 1.4%. Sorry, I didn't.
That's good.
Sorry about that. Yeah. And what is important is that our share of global emissions is not dropping. That's something to remember. It's not increasing, but it's non-decreasing, unfortunately. And all this is happening even though we have a good renewable energy use practice generally in telecommunications. And what is also important, we hear a lot trying to establish a correlation between data transmitted and energy used or GHGs generated. The correlation is not straightforward. Data rates grow much faster, whereas GHGs and energy consumption grows or doesn't decrease, let's say. So we need to make a distinction. And what is important, which will make a difference, is that per subscriber energy use is not increasing, but the GHGs are somewhat decreasing because we are using more and more renewables. However, subscriber numbers are also increasing. So we have to really balance. Thanks. Next slide, please. Now, a few words about the ICT sector. This picture is from an ITU, but it's generally accepted. What the user side means, what the network means, what the data center means, and what is excluded. And what I want to draw your attention to is the mix of greenhouse gas emissions that occur based on the manufacturing of equipment versus its use. So in the user devices side, the balance is 50-50, or if you take mobile handsets, it's really even more on the manufacturing side. Whereas for networks, the balance is really skewed. Our embedded emissions that are caused during manufacturing is rather low as compared to the use phase. So that's why we focus so much on reducing use phase energy consumption. And data centers and enterprise networks are grouped together, and there the picture is also similar. Next slide, please. So given this situation, as compared to other big industries like electricity generation, transport, or agriculture, buildings, manufacturing, our share of of the GHG emissions is low. Why should we still care about this? Next slide, please. There are plenty of good reasons, actually. And one of them is that the Paris Agreement, we all know this 1.5 degree limit humanity is chasing and is about to unfortunately miss, it looks like, has set targets for industries, and United Nations organizations have calculated the, let's say, responsibility of each sector. And for the ICT sector, they set a target to reduce emissions by half by 2030. And as I said, we are nowhere near that target because we are in a non-decreasing cycle. And also, there is a more practical reason. Most of the companies, vendors or operators have now net zero pledges that we are supposed to report. And also in Europe, for example, soon we will be required to report. And that depends also absolutely on the GHGs generated by the networks. And so you will hear this a lot. We are switching to renewables, so that will take care of things. Unfortunately not, because energy consumption is rising and both renewable and non-renewable energy use is also rising. So to reduce the emissions by 50%, renewable uptake will not make up for the gap. And another very key note is that we said per subscriber energy use is stable, but subscribers are rising. So 1/3 of the population is still not connected. So their connection to the internet, to ICT services must be done in a sustainable way. If we increase the subscriber numbers steadily, somewhat we have to decrease their GHG impact. And also, we have seen a disturbing trend in the ICT industry that new applications or new technologies like AI, metaverse, or digital twins are increasing ICT impact, unfortunately. We have seen very prominent companies announcing that their net zero pledges are no longer valid because the AI impact is pushing them to use more and more energy and resources. So there is a good reason to care. Next slide, please. Now, what are we supposed to do? We are working on energy efficiency, energy consumption, but is that enough? What else has to happen so that this work translates into real greenhouse gas emission reductions from our operations? Please. Okay, so this is the bathtub metaphor, which is very often used. And the idea is that everyone has to take care of their own bathtub. And we'll see what that means. Next slide, please. As I said, we are working on energy efficiency, but are we working on the right reason, with the right reason, let's say? Because as you will hear quite often, networking industry is focused on cost when it comes to energy efficiency, energy reduction, energy consumption reductions. Now, this is necessary, we understand, when we follow a, let's say, multi-dimensional sustainability perspective, you have to take care of the environment, but also the economy and the society. We have seen when we don't do that, we cut subsidies abruptly or forbid gas furnaces in homes, etc. Households react, farmers react, things don't move. So cost is important, affordability is important, or bottom lines are important, but do they result in the environmental impact in this case? We have to make sure, please. So I would say that a few other things have to happen. The path from energy efficiency to greenhouse gas emission reductions require a few additional considerations and actions. And of course, along with energy efficiency, energy consumption reduction, energy proportionality is a huge topic. That we said data versus energy is not directly proportional, or it's not correlated linearly, let's say. We have to get closer to that. Some people advocate zero energy for 0 bits, but this is largely, let's say, beyond reach. But nevertheless, that has to continue. So energy consumption has to come down. But we have to also take care of the carbon. So the energy supply that is used to power our networks have to follow a low carbon trajectory. And energy supply decarbonization and making sure that users and suppliers of data are also carbon aware. Everyone's pushing the onus onto the user, saying, oh, you have to decide when you watch this famous cat video. But what about the supply side? The content providers, content delivery networks, their actions actually dictate what the subscribers can do. So there are things on both sides. Then a word about traffic. We have heard this word on rebound effect. When you make something affordable, it gets used more. So we make energy efficiency, energy consumption, we make networks very cost effective from an energy perspective, but then they are no longer bottlenecks and they get used more. And we have to take care of this. There are practical things we can do about that. And infrastructure expansion. As we, let's say, grow the network, then it has an embedded emission impact, but also it is enabling more and more. It's like building autobahns everywhere, and as you build more, they get even bigger traffic. Thank you. So the rest, I can, let's say, I gave examples very quickly. We can go, I'm not going to go through them. It's for perhaps further reading. But in every domain, from energy to, let's say, GHG and environmental impact, there are things we can do on the network side in architecture, multicast, unicast, infrastructure sharing. These are all levers we can play. But what's important is, what is your priority as an operator that you can bring? And we can also prioritize beyond energy. Thank you.
Questions?
Thank you.
There's 5 minutes for questions. There's still 5 minutes for questions if you want. So there's still some time for questions if you want.
So you said it for 50?
Yeah.
Okay.
If there's Eric.
Thanks for the interesting talk. I think one thing that jumped out at me was the amount of the large percentage from the user device side of that. Like if that kind of adds up to 28% of the usage, if one of the biggest chunks is from user devices at use time. Is there things we should be looking at protocol-wise for cases where some protocols may use more power than others? So for example, some cryptographic ciphers or using quick over H2 might use more power, and in some cases you want them for performance. And right now, a lot of our selection of which to use is based upon performance.
Mm-hmm.
But it might be worth us looking at, are there cases where we want to kind of have the power consumption influence that? So if someone is close enough that quick isn't going to add much value, but it's going to use more power, maybe we should be looking at using kind of using H2 instead.
Mm-hmm. Yeah, indeed. We touch upon trade-offs very often. That performance versus sustainability, performance, energy, security, energy. These are indeed showing that we have to include the energy and the environmental parameters inside our equations or optimizations. And as you said, in many interfaces, perhaps the application of encryption might not be proportional to the risk, and that can be excluded, or a lower level of protection can be selected, favoring more energy savings indeed. But we have to understand that this is a, let's say, use case or end user question as well. We have to identify each case. What's the security risk? What's the environmental impact? And can we optimize together? And indeed, colleagues are working on this. One example I give is, for example, doubling the size of encryption keys, for example, for quantum readiness. And that, when it happens, it has a hardware impact as well, because on the UE side, you are probably forcing chipset changes on the mobile network, for example, UEs, and that is hitting the manufacturing embedded emissions from the UE side. And we have to ask ourselves, is that the right thing to do? And if so, if there is a risk for quantum era, then sure, but we have to all account for this. Does it answer your question? Yeah. Thank you.
Adrian Farrell, thank you for flagging up the Green BOF later in the week, which I have the dubious pleasure of co-chairing. A question that came up in relation to this, and maybe this room can help answer, is to what extent operators are willing to consider sacrificing SLA in return for power efficiency or power reduction.
Yeah.
I don't know if you've got opinions or if some of the operators here would like to throw rocks about that.
Yep. Yeah, exactly. This is exactly in the traffic management domain as well. In the past, people were okay with broadcast technology. Then everyone is now using on-demand. And that means unicast. And that's pushing video traffic to incredible amounts. And what's the impact? Let's say if you were to say we are scheduling a transmission every 10 minutes and you can join the next, let's say, session of video, you have to wait 10 minutes. That's quality of experience. Does that hurt your business? And if not, because that has a direct impact on traffic, on energy, on GHGs. So indeed, this is a key question, and that's the business side of sustainability. So it's not only environmental, it's also business.
Last one.
Jeff Houston, not really a question, but a comment. A much more pointed presentation was made at the North American Network Operators Group, NANOG, last month by Ron Bonica, also with Tony Lee, that pointed out that most networks are a bit like road networks. They're designed for about an hour a day of intense use. And the rest of the time you have an awful lot of resource unused. What you actually find is a huge amount of bandwidth, a huge amount of line groups and lasers, etc. And that presentation pointed out very, very effectively that if you're using multi-line groups, lag groups, if you simply turn off the excess capacity when you don't need it, the power savings are phenomenal. And so a lot of this is actually not about the bigger picture, but about the smaller picture. How do you actually design and craft your power to match your usage across a full cycle of usage, rather than trying to sort of take the macro picture and somehow reduce encryption, reduce this, reduce that, which I don't think is the way to go about it.
No,
So I'd certainly encourage you to have a look at that presentation from NANOG 90.
Sure.
And follow that.
Yeah, thanks very much. But I couldn't present the last 4 slides, which included indeed some of the measures you mentioned. Yep, thank you.
Thank you very much. The next presenter, Mark. And I'll put 15 minutes for the chat and 5 for questions.
Good morning. This is about the Internet Protocol Suite for deep space. Most of the content is on the draft that was on the first slide. That's fine. This talk is not about internet users and applications, so don't come to me and say, my browser application doesn't work for that use case. It's for, space applications. And this talk is not about near Earth, so LEO, MEO, GEO is not what we're going to discuss. This project is benchmarking with Mars, but will be implemented first on Moon, which is a quote, simpler problem. Next slide. You said 15 minutes, right?
Yeah, the timer's at the bottom.
Okay, fantastic. Thank you. Just a note to keep this in mind because it may have impacts on decisions or use cases. Space agencies now are moving into buying services instead of doing by themselves, starting with Moon. So quote, you rent a rover for a year. There will be comms and networking providers, and private sector will be offering various services to non-space agencies. We're moving from specialized equipment to RAD-tested commercial off-the-shelves or automotive grade components. Therefore, given that we have multiple providers, interoperability and governance will become strategic and paramount. Moon networking plan was defined by the IOAG, the Interagency Operations Advisory Group, and also for Mars to use 802.11, 802 whatever, and 3GPP on surface and orbit of the moon. Therefore, we'll be using IP. Next slide. Next slide. So, what are these space communications? Long delays. Earth to Mars, 5 to 20 minutes, one-way delay. So 10, 45 minutes round trip time, depending on the positions of the planet. And links are interrupted. Next slide. Why are they interrupted? Because we're orbiting, the planets are orbiting, and the orbiters are orbiting. So depending on the position of each device, you may communicate, for example, in middle line of sight between all devices, but if the orbiter is behind the Mars, then you cannot talk to Earth, but it can talk to the rover and the other way around. So you have to plan with, long interruptions.
Too fast?
Back,
Okay.
just a second.
Sorry.
The key point here is that relay or forwarders or routers need to store frames or packets until the next hop becomes reachable. So that's the key thing to do. It could be done on layer 2. That's what currently MRO and the other orbiters around Mars are doing. MRO, Mars Reconnaissance Orbiter. MRO is a 20 years old spacecraft, has a 40 megahertz CPU, but large solid state memory, and is forwarding the packets that are coming from the rover. And then for those cases, it stores the packets, actually the frames, for each of those scenarios. Next slide. So let's calculate a deep space RTT. For example, taking MRO again, MRO does essentially 15 minutes of communications every 6 hours, roughly speaking. So the smallest RTT would be a line of sight between everybody, and the planets are the nearest. So it's a 10 minutes RTT. A pretty large RTT would be where the planets are far away, and that you are not lucky, and you had to wait until an overpass to talk to the other guy, and then you're putting this really in bad shape. During that pass, you don't have time to, reply, so you take another overpass. I'm pushing the limit. So it becomes 13 hours RTT. Worst case is Solar-Mars conjunction. They are really in bad shape, so you have 2 weeks of no-com every two years. So in that case, the RTT is 2 weeks. Interesting problem. Obviously, if you have a constellation of orbiters, that could cover the whole planet, Moon, or Mars, then you're lucky, but that will take some time. Next slide. So Earth Moon is going, as I said, we're targeting Mars as the benchmark, but Moon is the one that will be implemented. It's a few seconds delay, not very long, but long enough that typical internet application won't work as is, will need kind of tweaking. And however, Moon for some time will have the problem of not enough orbiters to have full coverage like Starlink. Therefore, you will have interruptions of communications. Therefore, you need to plan for the fact that sometimes you'll have to buffer data frames or packets until the next opportunity happens of communications. Next slide. Okay, so the key point is, can we use the IP protocol suite for deep space? The answer, from RC 4838, that was essentially written 25 years ago, published in 2007, concludes no. And the very short summary is, TCP doesn't work in this context. protocols and applications are too chatty for delays and disruptions. Therefore, it doesn't work. The consequence was the invention of the new networking stack called the bundle protocol, based on a star and forward design. You need then to do everything, from scratch: transport, routing, naming, security, neighbor discovery, application API, network management. Somewhat, you have to reinvent everything. I was the co-chair of the working group for some time. A few years ago, I started to be concerned that we're not making enough progress, I would say, and it's difficult, and we can go into a lot of debate and discussion about it. So with a group of friends, veterans, people that we look at why don't we reassess the internet protocol for deep space given where we are today. And the essence of this work is documented in the draft and the subject of this presentation. Let's go next slide. So that's the IP stack, deep space IP stack. So you see TCP, no way. In space, in space, you will have CCSDS is the SDO for space communications and IT in general. Consultative Committee for Space Data Systems. They have defined space links, which are essentially layer 2 from the point of view of IP. We will have 802 something and 3GPP on the surface and orbits. So you will run IP, UDP. UDP has no notion of time, such as IP has no notion of time. And you could run the UDP applications protocols. You could use CoAP for IoT. And then you may be able to use Quick TLS, and then that gives you the rest of it. Next slide. In the scenarios that you can think of is like when the spacecraft is actually cruising, when the spacecraft is actually connected to a surface network, and then in the context of relays or routers or forwarders, they could be layer 2 relays or layer 3 relays. We're essentially assuming this for some time because it makes the design of the spacecraft, the relays, way simpler. Next slide. So IP has no notion of time. We did have TTL, but it's actually used as an up count as confirmed by V6. Can be encapsulated in CCSDS space links. It's already defined. Since IP over space links are point-to-point, we can use header compression, which means that you can compress a lot the IP UDP headers in almost a single byte. And the key thing here for IP stack, for forwarders actually, the ones that have interrupted links, is you need to temporarily store the packets. That's a new behavior for forwarders, because in a normal IP forwarder, if the destination becomes unreachable, you just drop the packet and send back the ICMP message. In this case, like if you do on, for layer 2, the MRO, you just store the packet until the link is back up and then you forward again. We did a prototype of this, 200 line of C code, no big deal. TCP doesn't work. UDP has no notion of time, so fine. Next slide. So I'm going to skip this in the sense that you should probably know Quick. But Quick has, even if it was not designed for deep space, actually has a lot of different interesting properties that are useful for deep space. One handshake for establishing the communication, zero RTT, user space. A single connection is a pipe of stream and can be long-lived. So you can imagine setting up the connection while the spacecraft is on Earth, then sending on space, and then keep the same connection for the time of the mission, month or years if you want. Next slide. So does quick works from for DSpace? Well, actually, by default, no. But if you set the, a few various quick parameters to appropriate values, which is essentially pretty large, based on the, expected largest RTT. So you kind of set the initial RTT, max idle timeout, window size, and you simplify the congestion control. Then quick works fine in space. We did multiple simulations on this. You could use quick with proxies. For example, you could imagine a deployment scenario when you do proxies at space edge, where the proxy itself would probably be more smarter in terms of access policies, buffering, QoS, and those kinds of things, while elsewhere will be kind of a unknown. So the quick clients and quick stuff on Mars may not know at all about deep space really, but only the proxies that at the space edge will be. Next slide. So we did some simulations. So we sent an HTTP request to Voyager, obviously in simulation. So for 48 hours RTT, we used the quick configured as I previously said, and then, it worked. Next slide. We tried 10 days RTT, and at that time, our simulation environment was not doing that was wall clock, so it was not doing time warping. So that simulation actually took a whole month to do. So, next slide. So what do you need to do if you use HTTP an application for deep space? Well, HTTP itself doesn't have any notion of time, so you're fine, unless you use cache control or expire headers. So either you don't use them, or you set proper values, but HTTP itself doesn't have notion of time. So the only thing that you need to care if you're using a HTTP environment is that you take the timeouts, right? You make sure that the timeouts on the client and the server sides are appropriately set for the RTT. And then you make your design asynchronous, And if you do, you have assets, you make sure that you use local references. Next slide. I'm going to skip a few. Next slide. So we did a few results. You have the slides on the, a lot of simulations actually, packet loss, reordering, all the transport semantics we tested. This one is packet loss of 5%, delay of one-way delay of 1 day. We repeat 10 times the HTTP request so that the packet loss is kind of applied over the whole thing. And, obviously the total time was the same as without packet loss because the recovery was done while the other request was sent. So it worked. Next slide.
Clear up a couple data. There we go. All right.
We're done?
No, well, your time's up, but you have 5 minutes for questions, and you have 3 people in line.
Okay. So we did test our implementation of storing packets. We did ping. Next slide. Next slide. Next slide. Well, you could do UDP. So therefore, you could do streaming over UDP or over Quick, or you could do even SIP. So you can call, Mars if you want. Next slide. And I think that's.
People keep getting in line and messing up.
Okay. Network services, and Warren, you didn't want any DNS. Well, I have something about DNS. So network management, you could do SNMP. We tested it work. You just set the timeout properly. NetConf is using TCP and SSH, so we need NetConf over Quick, which is being discussed this week, or RESTConf. I haven't talked about BGP or routing, but BGP over Quick may be useful. Jeff. And DNS, well, DNS is kind of isolated networks, or mostly isolated networks, so you need to be careful. So kind of a pre-caching stuff. There's a draft about this, and actually Warren helped me out in sketching the ideas around this. And I think I'm almost done in terms of slides. And if not, yeah, that's what it is. Next slide. So summary, store packets for the forwarding nodes that are facing links up and down, but only those forwarders, setting the quick parameters appropriately, and design your application to be asynchronous with large timeouts. Next slide. Questions?
Yeah, thank you very much.
There's a side meeting Wednesday morning.
Two questions. Is something like Quick the way you would design it from ground up if you would have to, do that? And the second question is...
That's a good question.
Yeah. Well, I mean, because I think that something like that should be explored. Whether that's feasible in the practical world is a different question, but it's always good to know how close you are to...
I was trying to reuse whatever we have in our tool set.
Right,
And
if it's
frankly, if you start having transport semantics, taking care of reorder, duplicates, and packet loss, you're probably going to reinvent. And then user space and one handshake for establishing a connection. When you start all those things, in abstract, you may end up pretty close to Quick, actually.
Well, maybe, I mean, I'm not sure how easy it is for Quick to do, let's say, forward error correction, so proactive, for the channel being lousy, for example.
Okay, good question. FEC there's a draft of Quick about using FEC. FEC is actually being used at the lower links already. And one of the reason of this is that mission operations have to send commands to the spacecrafts. And these are to be, it's like a small string, right? Reboot. These has to be pretty reliable. You don't want errors there. So the signal error rate is not good, but the frame error rate is very, very low because they apply two codecs in pipeline at the link layer. Therefore, the actual frame error rate is very low. So you may not need that much additional FEC on the top of it.
And then maybe I overlooked it in your stack, but don't you think that things like proxies, converters, caches also are going to play an important role to hide as much as possible the novelties of these type of links from legacy endpoints?
Yeah, completely. Well, you add a little bit of it when I talk about proxies. So yeah, caching, pre-caching of stuff. Yeah, completely.
One second, Rick. We need to make sure we use the hands up thing in the app. Like Neilani, just keep it super quick because you didn't use the...
I know, sorry. I need to get on the app. Yeah, I'll do it. I'll keep it really quick. So I'd like to see, we have a perform an extension header, IPv6 extension header, which might be helpful for you, performance and diagnostic metrics. Well, I'll talk to you after because we can help you measure some of this stuff much more lightweightly.
Sure.
Jeff Haas, nice presentation, Mark.
BGP over quick?
No, not a thing about BGP. I think that signaling this, routing and this stuff would be terrible. So one observation, one question. A lot of the protocols that you've had in prior slides are flavors of call and response protocols. Pick netconf as an example, even SNMP. Those things are going to work terrible in these sorts of environments. What sort of work have you done to say, here's stacks that we do that is old school modems? We start something and we push as hard as we can.
The way you're saying it, we haven't looked at that perspective. So I guess we need to, I haven't looked that way, so I'm not sure how to answer your question.
Okay.
Actually. So.
Yeah, maybe something to chat about.
Yeah.
So the second thing, so I haven't deeply read the entire quick RFC set because you guys keep on coming out, tons of them as you're going along. What should I be looking at RFC wise that talks about this type of sending discipline where we're not having data blocked actually causing usual flow control token issues?
You're looking at which RFC?
Yeah, which RFC should I be looking at that's not the core 9000?
Well, RC 9002 is actually about recovery and congestion control, right? So it's like where everything kind of work. Christian Itema and I wrote a draft about quick in space, which is actually a bit outdated from the time we wrote it to now what we've been doing. It's kind of due to be a new version, so you'll explain. So there's from our point of view, we haven't documented everything fully in terms of what we're doing. It's kind of sparse into presentations and simulation things, but
that's exactly what I'm seeing here, is that for this sort of thing that you've had to work, you have to be assuming that you're not going to be having flow control. You have to have some redundancy. You have to avoid flow control. If you have a prior draft, please drop it in the chat. Thanks.
Super quick, we're out of time. There's two of you.
Yeah, hi, this is Peter Thomason. So you showed some measurements of your simulations, and from what I can tell, it's pretty much, I guess, what you would expect by scaling the time axis or time units to, I don't know, millisecond corresponds to half a day or whatever. And then...
okay, I'll let you finish.
And then adding some random stalling. I'm more interested with my question in comparisons between like communication concepts. So you, for example, said TCP doesn't work well, and I understand. And then you said QUIC, however, seems to work well. And QUIC has some retry stuff like TCP does. So I wondered, why is that not a problem if it is for TCP? And then more generally, you were looking at IP stuff and said, okay, cool, we can do these experiments. And we don't need to use the network bundle or whatever the other protocol was called. But how do those actually compare? Why would we not just use the thing that was designed for deep space communications? Why do we want to continue using IP?
Okay, so there's multiple things about in your question. Quick, you cannot just expand the time because it won't work. You need to adjust is internal mechanics. So that's what I was saying in terms of setting a few parameters and simplifying the congestion control mechanism to be just the flow control itself. So that's what I was saying. If you don't do this, then it won't work, with long delays. So there's still within the RC specs, but we're kind of changing a bit a few transport config parameters of the quick implementations to achieve that. The other question about shall we use bundle protocol? Well, it's a long debate, and I think the next person in the queue will have maybe some other things to do. It's like any solution, there's pros and cons in each approach, and I think the IP approach, if you remember, we'll have IP on the surface and orbits of Moon and Mars. So and we have IP on Earth. So if you enable IP in the deep space, then you have a single IP network, right? A single networking layer everywhere. Makes things zillions easier to do than having all kinds of gatewaying between multiple, between bundle and IP and stuff. So, but we could have a long conversation about it.
Sorry, I know we are out of time. Just a quick comment and then a question. As Mark mentioned, there's a pretty big debate with BP and what is simpler. And BP to IP gateways might be simpler than carrying the assumptions of IP literally throughout the solar system. But one of the things that BP does is allow you to pick bundle by bundle when data is no longer needed, when it has been stored for too long because of waiting at intermediate nodes. And that was an important design decision because you don't necessarily want to keep data that has expired in systems, particularly in space systems where storage and the power associated with it is very much at a premium. In this approach, how do we determine that there are packets that should no longer be delivered and can be thrown away sooner or earlier?
Okay, well, we may start that debate again, but
Yeah. I was just, this sounds like a mailing list conversation.
Yeah,
Oh,
yeah.
okay. So, and if it's already been covered, I apologize, but that.
No.
I'm just saying we are way out of time. We're
Yeah,
gonna be rough
so-
getting to the end of the rest of them. I think overall, I would say super thanks for the presentation. I
Sure.
think a lot of people were interested, me in particular. I think there's a lot of stuff that could be done to, expand and move on, but maybe maybe right now is not the time.
Yeah, I agree. It's that question, there's debates between the two alternatives.
Yeah, sounds like
You
a
know,
lot.
you understand.
Yeah, thank you very much. Is there a Carlos in the house? Yes.
There's a Carlos over there.
All right, Carlos, you have 15 minutes for the slides and 5 minutes for questions, and hopefully we'll stay close to that.
Do you have clicky thing or I have to
Just
say
say,
next?
yeah,
Just
just
say
say
next.
So, morning. This will seem very boring after Mark's incredibly cool presentation, but I want to try to make it interesting. Next. Why I'm here, well, Carlos, most of you know me, perhaps some of you don't. I work for LACNIC, one of the 5 IRs. And my goal in this presentation is to bring some lessons we learned while migrating our RPKI CA to a completely new architecture and a completely new set of software. Basically, sort of a brain transplant of the whole RPKI system. Next. So I'm not going to explain what the RIRs are, just there are these organizations that have little black books where we write who holds which IP address. And the most relevant part of this for my presentation is that LACNIC, together with IPNIC, are the only 2 RIRs who have the particularity of having national internet registries under the main registry, right? We have the NIR in Mexico and the NIR in Brazil. That will be significant for what comes after this. Next. So basically what we have, the services we provide for users are basically through a web portal. We also have a REST API, and we have also delegated RPKI or up-down, depending on what term you prefer to use. This is how the members interact with the system, basically for ROA creation. Back in the day, we allowed some control over the certificates, the resource certificates themselves, but we basically try to hide much of that because actually there's little point in members operating over the certificates. For some reason, I would say 99% of all user interaction happens through the clicky thing on the web portal, which I sort of fail to understand, but whatever. It is what it is. So there's the registry database, which is the little black book with the IP addresses are. There's the CA, and then, and this is relevant again, we have under our CA, the delegated Brazilian CA, which is very large. It's actually larger than the main LACNIC one. Next. Why, I mean, some people may ask us why we decided to move to a completely clean slate design because of reasons. I could talk hours about this, but to make it short, the old system had been patched over and over again and features added over time. And at some point we decided we need a completely new thing. It was about 2 years ago. Next. I'm not going into detail, but this is what we came up with. Basically, we split the whole thing into different components. We modularized the interface with the central pool, the registry database. We created some command queues, and we split the CA in a couple of sub-CAs, plus a publishing system. So when we started to consider how to implement the different components you just saw in the last slide, at some point we had to be a bit, I would say, try to learn our own limitations and decide if we really wanted to implement a whole new signing CA ourselves. And even if we did that, if we could actually keep up with the work that is coming out of the ETF. And the a bit hard decision we made is that there is something that we can use that does most of it. It lacked some of the features we needed, but with the help of NetLabs, we could actually have them implement that for us. Next. So we try to avoid the not invented here syndrome that sometimes, permeates many of the organizations we work for. So we had some red lines during the migration. We wanted to keep the same TAL file because hopefully, currently right now, there is no way of rotating the TAL. There is no equivalent of RFC 5011 for RPKI. Hopefully there will be in, I hope a few weeks. The thing is, even when the RFC comes out, it will take time for CAs and relying party tools to implement that. We wanted to avoid long-running instances of relying party tools to have to reset their caches. And we had a expectation of doing a zero downtime migration of the delegated Brazilian CA. Next. Some of the challenges we found. RPKI, especially RPKI CA development, is notoriously hard to test because it's really hard to instantiate whole trees with dummy data, for example. Perhaps you can do that with Grill, but doing that with proprietary system can be very hard. It's a testing, doing good testing of RPKI tooling, it's kind of hard. We wanted to pre-test the integration with the member portal, and we would like to have the ability to have both the old and the new system running in parallel. And we wanted to be able to validate the strategy for migration we were thinking about. Next. So, things we learned. So, I would call them ideas that paid off in a way. When developing the interfaces with the member portal, we created the internal API that communicates the portal with the CAs into an internal API that actually can publish to multiple CAs at the same time. We did actually the last code modification to the old system so it understood this new API. And a year and a half ago, more or less, we started running both systems in parallel, the Grill-based system and the old system. We could have many of those, and I have an idea for that may be discussed with you during the week. Next. So the high-level idea of the migration will be to have the old and the new running at the same times, publishing on different sets of servers, and be able to switch between them using DNS, changing the DNS records, right? We started running the whole pipeline in parallel about October last year. We found a few bugs, actually. There was a funny one that was found during the Lightning event in Fortaleza in October and corrected during the week. Thanks, team, by the way. So the idea is once we're comfortable with the outputs of both of the old system being consistent with the new system, it will be time to change DNS records. Next. This was really interesting, and this took a lot of discussion and back and forth between the different parties. How to do the zero-time migration of the delegated CA. For context, Registro VR has been running on Grill for almost 5 years, if I remember correctly. And Grill supports the idea of multiple parents. Someone asked why just changing the hanging point of the CA from the old to the new is not enough. And the reason that it's not enough, it's because the service that Registro VR provides to its members is also delegated RPKI. So during the time that the third level of CAs go back to the parent and resign the repository, they will basically disappear from the internet. And that could take days or even weeks. And I will show you a graph. We actually got some numbers for that. So the idea was to use this feature that Grill supports multiple parents, add the new and the old at the same time. This is not why this feature was created, but it was sort of a welcome feature. It doubles the repository size, but the thing is, most of those repositories are kind of small, so it's not a big deal. Next. So the end, I mean, the final component of all this is this gonna work, right? Once I change DNS records, long-running instances for relying party tools will be happy with just seeing a new RRDP session and keep on chugging happily or not. And this proved a little bit hard to do because we also wanted to test different versions of relying party tools. So lesson learned here, Docker is your friend and DNS mask is your friend. I don't know if many of you know what DNS mask is, but it's a really cool tool that I discovered during this. Basically, it's a sort of smallish DNS server that you can use as a proxy DNS or a local resolver, caching resolver, or you can use it to insert records, arbitrary records that, whatever. It's sort of an etc hosts as a service or something like that. It also can be controlled automatically from a script. So we wrote some scripts that allowed us to run Docker instances of whatever I had a Docker instance for. And actually scripted the back and forth in the DNS between old and new, old and new. We learned a few quirks about how Docker actually configures DNS resolver for the containers, but there are switches you can use to override that. And we actually tested these 3 relying party tools all the way back to the earliest Docker image that was available for them. And I don't have the numbers exactly here, but for example, for Routinator, we had like a almost 5-year span of version that had Docker images available. Fourth, we had Docker images also going back almost to 1.0. And RPKI client, there were like a good 2.5, almost 3 years of versions that had Docker images. So it worked. We were quite happy with the result. We find a couple of things that were easily corrected during doing tricks on the server side, like doing touch on the certificate, because some of the versions of these relying party tools will not re-download the certificate because they thought it had not changed or something like that. Next. This is a timeline of what I described. This is in the order that things happened. And this graph that I included down below it shows the moment where the second parent for registro VR was added. And you can see we start from the 16,000 something VRPs that the pure LACNIC repository has. And you see this ramp up while the delegated CIs from registro VR go back to their parent and resign the repositories. And they become visible under the new tree. It lasted for about a day and a half, and there was a slower ramp up that lasted for days. Next. So at the end, the final part of all this was trying to keep all the parties, the stakeholders, I would say, updated on what we were doing, communicating with them. And actually, I asked for help to many of you, and thank you for that, actually. I don't think that, we would have, the nerve of doing this without, having the back and forth with many of you. So thank you for that. In the end, when we did the migration, it was a bit of a letdown because in the end, the whole migration lasted like for 30 minutes because it was just, shutting the old system, changing DNS records and wait for it, and it just worked. But again, thank you for all your help. And again, I brought this because, I don't know, maybe some of these ideas may be useful from an operational perspective for other people operating CIs. So I think that's the last one. Thank you.
Great, thank you.
If there's any questions, there's 5 minutes for that.
Hi. Sorry. Tim Reusels. Ripens to see these days, but in our lab back in the day when this was ongoing. I wanted to just make an additional comment on the strategy to have both systems run in parallel and add a additional parent at the level of NIC PR. Another reason for doing this is that it would be much easier to revert as well in case of issues. Because otherwise the communication between these systems could become very confused when suddenly you think you're talking to your old parent, but they're actually a new parent, and you want to go back, and then all kind of things can go out of sync. So that's a thing to keep in mind for these things.
Thank you.
Good, great. Sorry, I have a sort of comment for you, or question. Me, I do. Chris. Sorry, Chris.
I was you're not on the tour.
Yeah, sorry, Chris. I didn't put myself in the queue, so I'll ding myself for that too. I work for Google and do security stuff. Anyway, you said in the early part of your talk, like testing this is really hard. I don't really understand anymore why it's so hard. So like, should the Cider Ops group or somebody be saying, decompose this whole thing down better and then try and work out how to get the parts tested? It's not just that RPKI client and Fort might do different things. They may, and that's a problem that could, I just picked two things by happenstance, by the way. I don't actually have any idea what any of them do. Like, is this not a problem that could be decomposed and then some framework for testing this could be built? Like making certificates is I don't have a shell script that does that. It's not hard, right? Like, I don't really understand why it's so hard.
Because there's no really good tooling for example, creating fake repositories or introducing control failures. I don't think it's it could be a Cider Ops topic, but I'm not sure it's actually a protocol problem. It's rather a software issue.
Cider Ops is an operations group. It's not a protocol group, which
Maybe
somebody in the group will
something.
be happy to tell me 3 times.
Okay. So yeah, I don't think that's, we could discuss that in Cider Ops. I would say something along best practices for RPKS software testing or something like that.
Okay, thank you.
Thank you.
Which one's this?
This is DNSSEC.
DNSSEC,
Test and
okay.
post-quantum. I think it's our last one. I hope it's our last one, or we've messed up the time.
The timer will be down at the bottom in a second.
Okay, hi, it's Peter. I'll give you a quick presentation on our post-quantum DNSSEC experiments with various algorithms in the field. It was a RIPE Atlas study. Did it together with Jason, who's sitting there with a red cap for to be recognized. Okay, next slide.
No, sorry, I stopped.
Or do you want me to?
Nope, I got it. Sorry.
Okay. All right. So in 2022, we did another study with just Falcon implementation in Power DNS. And we wanted to expand that and do a field study with an actual public deployment. The Power DNS Falcon thing was just local Docker things and internal measurements. And yeah, so we implemented in Power DNS and in Bind various post-quantum signing schemes and put those on the public internet so that one could do one's own queries and see how it goes, but also do queries from other vantage points from RIPE Atlas and then do statistics on them. We implemented both signing and also validation, so one can interoperate, for example, validating bind signatures with Power DNS and the other way around. The measurements were parameterized along a number of dimensions. So for bind, we used a KSK-ZSK setup, which is essentially having 2 keys, and one of them being kind of an intermediary to the other. And for Power DNS, we used just 1 key, which is called a CSK scheme. Then we also looked at domain names, like we set up our test zones and then we queried names in them that existed and also names in them that did not exist, which in DNSSEC causes a response that has a proof of non-existence. And there's various ways of configuring that. There is NSEC and NSEC3. And for NSEC3, there is in Power DNS the narrow mode and the conventional mode in both Power DNS and Bind. So we use those 2 different parameters also because they impact response size. Then we did queries through UDP and TCP, and we also did set the DO bit or did not set the DO bit. If the DO bit is present, that means that the client is interested in DNSSEC stuff. So the resolver will request it from the authoritative server, again, increasing the response size. And then let's see how it goes. So next slide, please. Here is an overview of candidates for post-quantum signing. It's taken from a paper by Moritz Müller, who did a study, I think, in 2020, about which algorithms might be useful. We focus on those that have public keys and signatures below 10 kilobytes, which already is pretty large for the DNS. And we didn't look at things that have like, I don't know, picnic with like 34 kilobytes, which seems hopeless. We also, for the sake of fanciness, included a stateful hash-based scheme that does have larger signatures, but why not? So it's called XMSS. Next one. We did implementations using liboqs, which is kind of an open SSL thing for post-quantum algorithms. We used Falcon 512 as before, but also for bind, not only for PowerDNS. When we added dilithium to the name server stuff, we added Sphinx Plus and we added XMSS in 2 flavors, once with Merkle trees and once without Merkle trees. And there is all kinds of parameter sets which depend on how many signatures you would like to be able to do before it gets insecure. That's related to the XMSS state. We can talk about that later if you have questions. Then we went on to RIPE Atlas and used about 10,000 probes in May 24 to run all of these different combinations. It was roughly 2 million queries. Thank you for everybody who donated RIPE Atlas credits, in case anyone's here. And we recorded the return code of the DNS response. We recorded whether the response was correct. With correctness, we mean that for non-existing names, actually an X domain status was returned. And for existing ones that we did query A record, that we actually did get the expected A record content and also the expected no error code. We did not require, for example, that validation was done in order to call the response correct. We also recorded whether the AD bit was present in the response, which is present if the resolver wants to indicate that validation was done. And we recorded response time for the sake of completeness, which I'm not going to present though, because it's not very interesting. We pre-selected results to make more sense of them. First of all, there is some noise in RIPE Atlas. Some probes are, I don't know, in weird setup environments. So they don't even they don't even do insecure DNS correctly. So we excluded those. We required that any probe resolver combination would have a correct response for algorithm 8, which is RSA SHA-256. If you don't have that, then you don't have, let's say, old school DNSSEC in a proper way. And if we don't have that, we don't need to talk about PQC DNSSEC. We also excluded resolvers from private IP ranges like 192, 168, and so on and so forth. Those could be valid resolvers. If they run the local network, that's fine. But RIPE Atlas can't query them over TCP because of some limitation in their stack. And to make things comparable in terms of how the sample is selected, we applied the same restriction to UDP. We also didn't look into network errors like destination unreachable and that stuff. We just ignored it in our result sample. Next slide. Yeah, so this is kind of an example of the queries that we did or that RIPE Atlas did. So this is with the d-obit set, the lithium query for PowerDNS through the Google public resolver. As you can see, the response flags in maybe line 7 or something don't include AD, so Google admits to not validating our dilithium implementation. And you can see in the RRSIG record that we use algorithm number 18, which is not from the private range. It's an unallocated non-private number. We use such numbers because we wanted to make sure that it looks like any algorithm that a resolver might not support, but we didn't want to risk getting special treatment because of private range. Next slide. So I will show you 8 diagrams in total. This is 1 diagram, not 4. And I will tell you how they're organized, and I have some notes here, what I want to say about them. So the first, the upper row is always UDP queries, so it says TCP false. And the lower row is, did I say upper? TCP? I want to say upper is UDP and lower is TCP. The left column is with the DO bit false, and the right column is with the DO bit true. And we're looking at the bind implementation here. You can see in the title, vendor is bind, and is NX is false, so this is for an existing name. And you can see that the response code is no error in 100% of cases of RSA SHA-256, which is our pre-selection, so that's plausible. And overall, surf fail doesn't really occur for classical algorithms, and it does occur for the PQC algorithms as response sizes get larger, and it happens to be the case that as you go down in the algorithm dimension, response sizes get larger, so surf fails go up roughly. You can see if you, for example, go from UDP to TCP without the DO bit set, delivery rates increase, so surf fail goes down. If you look at XMSS, for example, about 30% in the top left quarter and only about 17% in the bottom left quarter. Yeah. Yeah, okay, next slide. So this is the same thing for Power DNS, the only difference really being that now it's a CSK setup, so there's one less key. So a DNS key responses are smaller, and overall delivery rates are better. And especially for Falcon, you can see that the success rates are really high. It's 97% over UDP and even over 98% for TCP. Next slide. Now this is a big expansion of the algorithm space, it seems. So what it actually is the same algorithms, but there is one NSEC and one NSEC3 for each of them, because now we're asking for a non-existing name. And again, you can see it's fine for RSA 256, which is our pre-selection. And if you compare NSEC and NSEC3, hold on. Yeah, especially for dilithium 2, let me see where that is. Yes, it's, I will walk here.
Okay.
If you look here, you can see if you compare dilithium with NSEC, the failure rate is 38%, and if you do NSEC3, it's 43%. That's a small difference, but the difference is larger than it is for other algorithms, and that seems like some boundaries crossed in terms of deliverability, reliability. When you do that, there's all kinds of boundaries, MTUs, and all kinds of things. It seems like specifically for this setup with CSK, KSK setup with bind, if you go to NSEC3, then some people start getting more problems. So the bottom line of this is it depends on all kinds of parameters, and you get interesting explainable behavior. Yeah. So next slide. This is with Power DNS with a different kind of NSEC3 setup, which is the so-called narrow mode. And there the interesting result is in the last algorithm, the XMSS. If you go from NSEC to NSEC3 there, you can see that failure rates actually go from 20 or 30% to over 50. That's because the message size then exceeds 64 kilobytes, which is not deliverable. So the only ones who do deliver it seem to not actually request it. Yeah, the next slide. So in this diagram here, we have whether the response was correct. So the left bin in each of them is response was not correct, right bin is it was correct. And we can see that it's roughly 100% correct responses for conventional algorithms and 70 or 80% roughly for the PQC algorithms. And if you go from UDP to TCP, generally things increase by or improve by around 10%. You can also see if you compare left and right that things go bad or worse if you set the DO bit, which is, because you're requesting DNSSEC records and then responses get larger. So most of the time, well, not most of the time, but it happens, you run into surf fails. So then the response code wasn't the one that expected, and correctness is 0. Next slide. Yeah, this is the same thing with just a little better numbers because there's just one key again in the Power DNS case. And you can see again that this improves things by roughly 15% on average. And notably, again, Falcon is doing pretty well. And then finally, we have the AD bit, which is on the next slide. This is really interesting. So if you use DO equals 0, then nobody really sets the AD bit because you're not requesting validation unless the resolver really wants to do it. But if you set DO bit then validation is requested. And for the classical algorithms, roughly 30–40% actually do it. That's in line with statistics from IEPG, for example, that say how many resolvers do validation. And for the PQC algorithms, validation obviously isn't done, except for Falcon, it seems, which obviously must be wrong, right? I mean, we're pretty certain that not 8% of RIPE Atlas probe resolvers do actually validate our Falcon implementation. And interestingly, it goes away if you use TCP. So it's not really clear what kind of software that is that does that. Next slide. Yeah, same thing for PowerDNS, no difference. Next slide. Okay, so the main takeaways of this are, I'll not go through it really in case you want to look up the takeaway numbers. Slide 14 is the one you want to look at. Next one. Yeah, this is a benchmark done with PowerDNS for the different algorithms, the classical one at the top and the PQC ones at the bottom. Left column is keygen time, then there's signing and validation. And the takeaways are essentially that for Falcon, things are in keygen time several orders of magnitude better than, for example, RSA. It's on par with algorithm 13, for example. The scale is logarithmic. And signing and validation is fine in terms of time. But for example, if you look at Sphinx, then signing is pretty long. It's like 0.2 seconds per signature. And specifically for XMSS, it's prohibitively expensive to generate keys. It takes several seconds. So not only the message size is a problem, but it's also not suitable for generating keys ad hoc. Next one. Yeah, so this is the same query as before, except we're not using a Google Public Resolver, but we're now using our bind validation implementation to validate the PowerDNS dilithium signature. And it's the same response as earlier, except that the AD bit is now set. This runs on port 5304 of our test server. If you use port 53, you will get to the authoritative server, not to the resolver. So we have set up these things. You can query all of that yourself in various combinations. There's a website that explains how it works. I think it's on the next slide. Yes, there it is. It's pq-dnssec.dedyne.io. And you have like a nice form where you can select query thing, DNS key, or A, or whatever you want. One of the algorithms, classically, or PQC. And you can select which vendor you want for authoritative or for resolver. You can select whether the name you're querying is existing or not. And if it doesn't, NSEC or NSEC3. Then you hit query. It goes through a DOH proxy, and you get a dig kind of output at the bottom where you can see how things actually behave. And you can also use your command line to do this. So this is the real deployment that was used by the RIPE Atlas study. I think that's it. Next slide is the thanks slide. I want to give a big shout out to Jason, who did the hard lifting, and happy to take any questions.
Hello, hello. Robert Kishtaki from RIPE NCC, providing Atlas for 14 years now. Thank you for this. It's lovely. Not a defense, more like a justification. You cannot ask DNS queries against resolvers on the private IP address, not privacy 1918 and such like that, because it would let you evaluate the local network, and we can't do that. But you can use the probe's own resolver, and for some of these questions, it may or may not be useful. But I'm happy to talk to you offline about details if you want.
Yeah, we can talk about it. So we only used the probe's own resolver. So because we wanted to do whatever the probe would do in a real setup. And from what we learned from talking to folks was that over TCP, even if the probe's own resolver is in a private range, then it won't do the query. But if it's a UDP query, it will. So actually, we had to exclude those measurements, but we can take it offline perhaps. And maybe I misunderstood that aspect. Queue's empty. Everybody hungry? Or everybody distracted from Biden's news?
News doesn't care in Canada. Okay, thank you.
All right, thanks.
Yeah, thank you. This is great. So, thank you, everyone. This brings us to the end of the IEPG meeting. Keep in mind, we will, as always, have another IEPG meeting at the next IETF. So if you've got interesting operational stuff to talk about, please do so. Also, if you've got any feedback on this, any of the presentations, come along and talk to Chris. or myself. Thank you again, and I will send the slides to Jeff, who will kindly post them for us on iepg.org, because thank you.
Yes, they are. I believe so. I think so. I believe so.